So welcome to the third lecture of the FIK3507 course Statistical Problems in Simulation. In this lecture we're going to discuss output data analysis and parameter estimation issues in simulation. I who will be presenting this is Jens Zander. I'm a professor in radio communication systems at the Department of Communication Systems at the School of ICT at KTH in Stockholm. So what is simulation output data analysis actually about? Well, let's return to lecture 1, where we had our mathematical model of our complex system, as we see in the middle here. And in a stochastic simulation, this is a piece of software that models our system and that is driven from the left by stimuli, which are usually random data or random variables. And on the output side, on the right-hand side, we get a sequence of x1 to xn, a sequence of output data, which of course then will be random numbers. Normally, we are not so interested in all these random numbers. Actually want to say something about the statistical properties of these output data. So we see these x1 to xn as observations of a random variable f with a distribution or density function fx, which may contain some parameter, known or unknown parameter theta. And in case it's unknown, we are interested to know more about that. And the technique we're going to use is to estimate this parameter. There are several popular examples of these parameters. It could be probabilities, it could be moments, for instance, like the expectation or the variance of x. The simplest way to provide such an estimation is the so-called point estimate. We have our actual unknown parameter theta, and we would like to find an estimate, single point estimate theta hat, single value that estimates theta. And what we have at hand is the output data x1 to xn. So we put it into a function g, and that will derive the point estimate theta hat. So this will be a single value. And since the x1 to xn are random variables, so random numbers, then also theta hat will be a random number that hopefully gets as close to the real value theta hat as possible. The performance of this estimator is how accurate it may estimate the actual value theta. And there are two ways of measuring performance. One is the so-called bias, and that is if you look at the expectation of this random variable theta hat and look how close it is to the actual value of theta. And if this expectation theta hat is actually equal to theta, then the bias will be 0, and we talk about an unbiased estimator. The other type of performance measure is the error or the mean square error of this estimator, and this is basically the variance of theta hat and how big is the spread around this actual value theta. Unfortunately, most cases we don't know the distribution of x, so but that's not usually a big problem, because we can estimate the mean square error by s squared, which is the sample standard deviation squared. And if we do that, we have removed the dependence on the a priori knowledge of the distribution of x. The graph in this figure shows a very simple example of how point estimates and the error performance can be used. We have observed our system for a number of cases here enumerated as z equal to 1 to 7. And for each of these cases we have made a point estimate here. These are the blue dots. And in the graph we also show the error bars, which are indicating the range of plus minus, range of deviation of plus minus s in our graph. For instance, in this particular example, we want to show how likely it is that all these points can be represented by a straight line as a function of z. And here we can clearly see that all the points lie within one s of the straight line. So let's be a little bit more concrete and look at one example. We have an observation vector x consisting out of 20 random observations, random integers. And our assumption is that these observations xi, they are random variables that are independent and identically distributed. And our task is to find an unbiased estimate theta of the expectation of x. It's probably one of the most common types of estimates we want to do. So how do we do that? The probably most common estimator we can find is the using x bar, which is the arithmetic mean of the observations. And if we, or the average of the observations, and if we do that, we get approximately 3.2 as our point estimate of the expectation. Is this an unbiased estimator? So let's calculate the expectation of theta hat. And as we can see, since we can interchange the summation and the expectation operator, we can see that the expectation of theta hat is exactly the expectation of x, which is theta. So the bias of this estimator is 0. And what about the variance performance? It's easy to calculate. It's simply the variance of x divided by n. That we know from that the arithmetic mean has a variance that is dropping as 1 over n. And since we don't know the variance, we use the sample standard deviation s instead as a compute there. And the s squared divided by n will be our estimate of the variance of theta hat, and this will give us approximately 0.168, or if we take the square root, we get the sample standard deviation of theta hat is around 0.41. The observations here were actually derived by rolling a die 1 to 6, and so the exact value of expectation of theta is 3.5, so it's not too bad estimate. And so based on this simple example, we can now make two important observations. First, the good news. The mean square error can be made arbitrarily small by simply increasing the number of samples. We saw that the variance drops as 1 over n, or the standard deviation drops as 1 over the square root of n, where n is the number of observations or samples. The bad news is exactly the same. The standard deviation, although it approaches 0, it drops only as the 1 over the square root of n. And if you look at the number of simulations or observations we need to do to lower the error, if you want 10 times lower error, we need 100 times more simulation samples. So let's leave the point estimates for a moment, and let's go to the second type of estimation. And that's what we call interval estimation. An interval estimate looks like this. It is an interval a and b, and this interval is again derived as a function of the samples. Since x1 to xn are random variables, now we have two quantities, a and b, that we have to compute, and these of course will be random variables themselves. And the performance of this interval estimate, or confidence interval as it's normally called, is the confidence, which is the probability that the actual value of theta falls between these two random numbers a and b. This type of estimate requires the knowledge of the distribution of x. And the point estimate, we got away with only knowing the average and estimating the mean square error. But here we need actually to know the distribution of x. Many estimators where we have a large set of observations, we can use the central limit theorem, and the error in these estimations will have approximately a Gaussian distribution. Usually we don't know sigma here, or the standard deviation, so we use the estimate S instead, and then we know that we won't have a Gaussian distribution, but a close relative, the student t distribution, which is tabulated, and you can find the functions in most statistical packages to compute it. For very large n, this is the typical situation in simulation scenarios when we have hundreds or thousands of observations. The Gaussian approximation can be used even though we don't know sigma and have to use the sample standard deviation estimate. So we can use the Gaussian approximation instead of the student t. So let's be concrete again and take an example. We use the same observation as in our point estimate example previously. The vector x of the 20 integer die rolls, and we have now to estimate theta again, but we want to do it not with a single point estimate theta hat, but instead we want to determine an interval a/b such that the probability that theta falls in between a and b is larger than 0.9. And how do we go about that? The most common way of doing this is actually to use the point estimated theta hat, and to create an interval a/b in the following way, that it's centered around the point estimate theta hat. So it's the interval is theta hat minus z to theta hat plus z. So the problem we have is to determine z such that the condition on the probability above is fulfilled. From the previous example 1, we can get theta hat, the point estimate, equal to 3.2, and the variance estimate we both get that from example 1. So now, noting that x bar is the sum of identically distributed independent variables, we know that such a sum will approximately be Gaussian distributed. So also will x bar minus its expectation will be Gaussian distributed, again now with a zero mean. So we can define z, which is x bar minus its expectation, and if we divide that by the standard deviation, we know that z will be a Gaussian or a normal 0,1 distributed random variable. And here we can plug in s instead of sigma. S is our sample standard deviation. So now we can use this fact to compute the confidence interval. What is the probability that theta will fall in this interval? Looking at the Gaussian distribution or Gaussian density function on the right-hand side, we can see that the probability that theta will fall in the center, in the white area in the middle, between plus minus z. If that probability should be 0.9, then 0.05 is the probability that should be masked in the shaded areas on the left and right hand sides. So the probability of theta exceeding theta hat by z should be equal to 0.05. And doing this computation using the inverse distribution function phi for the normal or Gaussian 0,1 variable, we can compute the value of z here, and z turns out to be 0.8, and so the confidence interval AB has to be theta hat, which was 3.2 plus minus 0.8, which is the given below. So this is our final result. So now it's time for you to try this out. We have in quiz 1 a parameter estimation problem. We still use the same observation as in our previous examples. We have this vector x out of 20 die rolls, and we want to estimate the parameter that the probability that x is less or equal than 2. That is our parameter theta that we want to estimate. And you should also give the mean square error of your estimator. We'd like to give a little hint. When it's about estimating probabilities, it's usually a good idea to use an indicator variable z that indicates that the event we're interested in estimating the probability for actually occurs. So in this case, z will be 1 if x is less than 2, or less or equal than 2, and 0 otherwise. And we note that the expectation of z is exactly the probability that we're looking for, our parameter theta. So pause the recording at this time and solve the problem on a piece of paper, and then we'll be back shortly with the answer. So here is the solution. We have our vector x, and we compute the vector z, which for each element is 1 if x is 2 or less, in this case 1 or 2, and 0 otherwise. So we have the vector z as indicated in the slide. And since the expectation of z was equal to the probability we're looking for, we have a simple point estimator now, theta hat, which is simply z bar, which is the arithmetic mean or the average of the z's. And this time it turns out that the ones and zeros were equally many, so our point estimate of theta is 0.5. Note here that we have replaced the probability estimator with a simple average estimator. And we can compute the variance in a similar way as we did before. So the variance of theta hat is simply the standard deviation, or the sample standard deviation s squared divided by n, since we have n terms in the sum. And we do the straightforward computation, and we find out that the sample standard deviation for theta hat is 0.11. And that concludes quiz 1. In the estimators so far, we haven't been concerned with the distribution of the estimator. It hasn't been needed. You can say we have a classical point estimation problem where we have an observation x1, x2 to xn. That observation vector has some distribution fx, known or unknown, and that distribution has a parameter theta, which we are interested in estimating, and we do this with this point estimate theta hat, which is a function of the observations. The mean square error is then simply computed as the expectation of the point estimate minus the real value, and we square this, and that is not a big problem if the estimator we're looking for is a average type estimator or expectation estimator. Then we know that the error is Gaussianly distributed, and the mean square error can simply be estimated by the sample standard deviation. We know that the Gaussian distribution is completely described by its average and mean, and if you have an unbiased estimator, the average is 0. So the only thing we need to know is the standard deviation, and that can be estimated by S. But for other types of estimators, it's not obvious how we should do this calculation of the mean square errors. So if we need the explicit distribution to compute the mean square error, why not estimate it? And that procedure is usually referred to as the bootstrapping algorithm. So we have an unknown distribution, and to estimate it we use an estimate FI of x, which is called the empirical distribution of the observations x, and it's simply a cumulative histogram of the observation. And we have an example here on the right, which is exactly the vector x in our examples 1 and 2 and in quiz 1. So these are the distribution of the number of die rolls. So you can see that we approximate the empirical distribution. The correct distribution, of course, should be a straight line going from 1 to 6. And in order to compute the mean square error, now we use the empirical distribution to compute the expected error. And this is usually called the bootstrap approximation of the mean square error. And from the law of large numbers, we know that these cumulative histograms will approximate the exact distribution better and better as the number of observations grows. In practice, it may sometimes be difficult to actually make this computation of the expectation. So why not use simulation? So what we do is that we first use all our data to approximate the distribution FE to get this cumulative histogram. And then we divide our observations into blocks and use the first n observations to make compute one estimate of the mean square error, call it y1. And then we use the second block to compute the second estimate of the mean square error, and so on. And then we simply take an average estimator to get an estimate of the mean square error. So this brings us to quiz 2. As usually, there are 4 statements. Some of them may be correct, some of them don't. It could be multiple correct answers. And please, again, pause the recording to figure out which are the correct answers. And when you've done, you press play and we get to the correct answers. And here are the correct answers. The statistical error in simulation results can be arbitrarily small by just increasing the number of observations. That's true. The distribution of a random variable has to be known in order to produce a valid interval estimate based on an average type estimator. That is not true, since for reasonably large sets of observations we can use the Gaussian approximation, and we only need to know the expectation and variance of the error, and we can use the sample standard deviation to make these types of estimate. Bootstrapping is a technique to reduce the variance in a point estimate. No, it's not. It's a technique to estimate the mean square error by using the empirical distribution based on the data. And the student t distribution is used to determine interval estimate and if the sample size is small, and that is also correct. If the sample size is very large, we can use the Gaussian approximation straight away. And again, if you've missed any of the questions, it may be a good idea to review the previous part of the lecture. And this brings us to the second part of this lecture, which is on time series analysis. And here we will treat correlation between different observations. In our previous analysis, we have assumed that samples are independent. So the vector x1, x2, and xn consists of independent random variables. We have used average type estimators of this type. Theta hat is an average of phi of x. And for these type of estimators, we can compute the variance in a simple way. It's simply the variance of the individual variable x divided by n, the sample size. And we can see that the variance decreases with 1 over n, or if you look at the standard deviation, it will decrease as 1 over the square root of n. Now, what if the samples behave as in this figure. So we have our samples can be seen as drawn from a observation from our system at times t1, t2 up to tn. And they behave like this. And this is a typical example of where the samples exhibit a strong positive sample correlation. So that if one sample is large, then a subsequent sample is also likely to be large, and the other way around. And in this case, the independence of variables is not really a realistic assumption, and we have to deal with the correlation between the different data. So let's look at what the variance of our estimator looks for the correlated data case. We can compute the variance in the following way, same way as in the uncorrelated case. You can see that the variance will be a sum of covariances, and in the uncorrelated case the covariances will all be 0 if I and j are not equal, and will simply be equal to the variance if they are equal. So in this case we have both the terms that correspond to the variance, which you can see here in the final expression as sigma square over n, and then we have an additional term here to the right that corresponds to the correlated data. And you can see if the correlation coefficients rho I are positive, then we'll see that this variance will always be larger than the original variance for the uncorrelated case. So we can do the same thing for the variance estimate. It looks like this. This is a sample variance estimate. This is how we compute it. And it's not so easy to see exactly what this computes to. It's a complicated expression, but we can see that for the positive correlation case, we can definitely say that the variance of theta hat can never be smaller than the uncorrelated case, which is the right-hand side, the expectation of s squared divided by n. But you can see also there's an extreme case when all the variables are correlated and the variance is basically the same as the variance for a single variable, which is es square. This corresponds to perfect correlation, basically straight lines. So after we have observed the first output data sample x1, we cannot learn anything more from observing the other ones because they're simply the same. So how can we deal with correlation? One popular technique is called batching, or sometimes it's also called interleaving, and we'll shortly see why. So how do we go about this? Well, we take our samples and we fill them into a matrix. And let's assume that we have km samples that we put into a matrix consisting of k rows and m columns. So what we do is we take our correlated samples and enter them into this matrix horizontally. So the first element x1 is in the upper left corner, and then the next element x2 will be in the second column, and so on until we have filled the first row with the first m samples. And then we take the m plus first sample and start the next row, and so on until we've filled in all the km samples. And then we process the data vertically. So what we do is that we read out from the matrix the samples x1, xm plus 1, and so on. So if the samples are strongly correlated horizontally, and if we have designed our matrix such that the correlation has basically gone to 0 after m samples, then xm, x1 and xm plus 1 basically will be independent samples or have very low correlation. So the samples we see in the vertical direction will basically consist of independent samples. So what we do is that we operate column-wise instead, and for each column will be a batch of low correlated samples, and we can compute the average. B bar, and so the ith batch, or the corresponding to the ith column, will have a sample average B bar that we can compute in the normal way, and then we can clearly see that each of these rows will have will be in the unbiased estimator of the expectation of phi of x, if that is what we want to compute. And we can also compute the variance. Now, instead of do it on a sample by sample basis, we do it on a batch by batch basis instead. So now we get a set of m batches, all of them with uncorrelated or basically uncorrelated variables. And of course, our estimator will be very good if the standard deviation will be low if these batches have low correlation. And how do we get low correlation? Well, we have to do a preliminary analysis of the correlation and have to design our batch size such that the samples in the batches will be basically uncorrelated, have low correlation. Another issue we're going to deal with is the initial transient or the transient phase of a system that we are observing. In many situations, like for instance in a queuing system, the behavior will look very much as in the graph on the left-hand side. The data during the first time period after starting the system has a very different behavior than the data that we'll receive later when the system has been running for quite some time. In the queuing system, this may be due to the fact that the queuing system may be empty when we start. And so for instance, the delay is very much lower at the beginning of the simulation. Normally, we're interested in the long-term behavior. We have an assumption that the observations that we do is from a random process that is stationary, meaning that the parameters of the process do not vary over time anymore. And obviously they do at the beginning of the simulation. So what we want is the stationary parameters, the time-independent parameters of the process. Unfortunately, it's not obvious how to do this observation. We can, of course, very straightforward, we can discard some samples at the beginning that we say belong to the transient period, and then only use the samples in the latter part of the observation interval. Let's say that we discard the first D samples and only use the n minus D later samples. And this is of course due to the fact that there is no definite end to the transient period. And there are a number of ways how we can choose D. If we have a lot of samples available, then of course we can make D very, very large, and so we can be pretty sure that the effect of the transient period is limited. But if we have a limited number of samples, this may be a little bit tricky. And there are a number of ways of doing this. One way, if we have very, very few samples, is of course to try to minimize the variance. We try different Ds and see what actually minimizes the variance of our estimator. And there's a trade-off, of course. If we have small D, then there will be an effect from the transient period. We take sort of transient data into the sum, and which will distort the data and also the estimate, and increase the variance. If we discard too many, if we increase D too much, then there will be very few samples, and the variance of the estimator will be high of that purpose. And also we can just do an observation similar as to in the figure and see when the process looks to be reach a stationary state. And this is usually a simple thing you can do if you have very, very many samples to work with. A final issue we have to worry about is the ergodicity of the process that we study. Normally we assume that the process that we study as output from our simulator is an ergodic process. And what is an ergodic process? Well, an ergodic process is a process where all the relevant statistic parameters can be estimated by observing a single realization. So if we start a simulator and if we just run the simulator long enough, we can get arbitrary good estimates of any of the parameters of the process. To stay clear of some of the pitfalls regarding non-ergodic process, let's give you an example of a non-ergodic process. Let's look at this example where we have a stationary noise process W of t that we feed into an amplifier with a random gain y. So the output x of t is the output signal from this amplifier. And if we look at two realizations of this process, it looks like this. So for every realization, we pick a random amplifier gain y. And we get, for instance, if we pick y in a certain way, we get the black dots, and if we pick y in a different way, we get the white squares. And it's obvious that if we look in one realization, let's say the black realization, we can observe this forever. It won't give us any more information about y. We get only a single estimate of y, but by just observing it more and more won't improve our estimate of y. So the only way to get information about y is to look at multiple realizations. So we have to restart the simulation several times and get different y's. So let's wrap up this lecture by another quiz. Again, we have 4 statements, and we suggest that you pause the recording at this point and figure out the correct answers. Again, several answers may be correct, and when you have your answers, you restart the video to find out the correct answers. And here are the correct answers. If you have simulation data with positive correlation, the variance will be higher, and we need more simulation runs to achieve the certain statistical error that we want to, compared to if we had independent data. So A is correct. B, batching is not a technique to estimate parameters in non-ergodic process. Batching is a technique to deal with correlated data. C is also correct. In a non-ergodic process, we need many realizations to accurately estimate some of the parameters. And D is also correct. If we want to eliminate the effects of transient behavior, we may discard some of the initial simulation data. And again, if you have missed some of the questions here and didn't get the answer correct, it may be a good idea to review some of the previous parts of the lecture. And this concludes the 3rd lecture.